Muhammad, and today I'm going to talk about the Laplace transform. So I hope that this interesting video to add some information to you regarding the Laplace transform. Okay, so let's go to the Laplace transform definition and notation, and we are going to give some important definition and notation for this transform. Okay. So first of all, the definition. The Laplace transform is an important tool for solving certain kinds of initial value problems, particularly those involving discontinuous forcing functions, as occur frequently in areas such as electrical engineering. So this is the first thing that we need to take care of, that it is for those who are interested in electrical engineering and they are going to major into this field. I think that Laplace transform is going to be of great interest for them. Especially that in electrical engineering, as we said here, it is you are going to face a type of functions that is discontinuous. So you're going to find something like you're working with things like this, intervals. There are some discontinuity, and we need to work with such kind of functions in an easy and convenient way. This is why Laplace transform is considered a nice and very convenient way for dealing with such kind of functions. Another kind of importance for Laplace transform, that it is also used to solve boundary value problems. Okay, boundary value problems involving partial differential equations to analyze wave and diffusion. So this is for wave and diffusion phenomena. This is also important for who are going to be interested in such area. Okay, now let's go to the next one for the real definition and the importance, or we can say the concept, okay, of the Laplace transform. We will see that Laplace transform converts the main issue, the main idea of Laplace transform is it converts some initial value problems to algebra problems. This is the main thing. So we are dealing with a transform, a tool that is going to transform the initial value problem or the differential equation, as we are going to see, to an algebraic equation, to an algebra problem. Commonly, algebra problem is very easy to be solved. So this means that Laplace transform is a quite powerful tool for making the initial value problems of differential equations to be easier to be solved, okay? Leading us to attempt the following procedure. So the procedure that we are going to follow to solve the differential equation using Laplace transform is going to be like this, especially initial value problems. We're going to start with the initial value problem in the first place. After that, using Laplace transform, we're going to change this initial value problem to algebra problem. And after that, we are going to solve the algebra problem. So this is the formation. Second, the solution. We're talking about algebra problem, okay? And after that, the last is transforming again to the initial value problem, and it will be very easy to obtain the solution of the initial value problem. So this is the third step. This is the common procedure that we are going to face in solving differential equations using Laplace transform. This is often an effective strategy because some algebra problems are easier to solve. As we said, it is easier for us to solve the algebra problem, as we're going to see now, than initial value problems. We begin in this section with the definition and elementary properties of the transform. We're going to talk about some definition and elementary properties of Laplace transform. and then actually this video is dedicated for this, only for some definitions and elementary properties. Maybe from the next video, from the next lecture, we're going to talk about how to transform between the two and how we can transform between IVP to algebra problem. Okay, now let's go to the definition itself. The Laplace transform of a function f, small f as you can see, take care of the being lowercase, is a function. This is what we call it Laplace transform. It is like L of f. Between the parentheses there is a lowercase f, defined by Laplace transform of the function for a variable s. We're going to look and think about this also, is the integration between 0 and infinity for this integration, for this form, which is e to minus st. So now it comes s. Why we put s? Because the definition of the integration of Laplace transform has this e to minus st times the function itself. So we are dealing with an exponential function defined as e to minus st, and then we are going to multiply it by the initial function that we have, which is f of t, our initial function, and we are going to integrate this multiplication, and we're going to integrate it with respect to our parameter t, this integration from 0 to infinity. Well, this is the integration, and this is what we call it the Laplace transform of the function f. But we need to have condition for this integration, that it should converge. Okay, it should converge. Some integration, they are not converging. We are dealing the condition for us that this integration should converge, and this is what we are putting here. The integration is with respect to t and defines a function of the new variable s. It is a new variable for all s such that this integral converges. So we use this new variable s such that this integral would converge. Because the symbol, okay, so don't worry about the definition. Maybe it's a little bit awkward, a little bit difficult, but you're going to find that it's super easy when we are dealing with the examples. Now let's go to the annotations and the notations of this Laplace transform. Because the simple L of f and with the new variable s may be awkward to write in computations, we will make the following convention. We will use lowercase letters for a function we put into the transform, and the corresponding uppercase letters for the transformed functions. In this way, we're going to say Laplace transform of f, it's lowercase, means that it is the main function. So it is going, the Laplace transform of the main function is going to be uppercase f, as you can see, uppercase f. And if we're going to deal with an input function g, then Laplace transform as g. If the input function is h, the Laplace transform is going to be h. It is uppercase. Okay, so whenever that you see something like h, this means the input function. But whenever I put h, this means that Laplace transform of this function. Okay, take care of the upper or the case of the letter, okay, and so on. If we include the variable, these would be written, if we're going to include the variable, the input function, this is the input function, with the new variable s. So we're going to put f, and between the parentheses, it is going to be s. So this is the same, they are equivalent. This one is equivalent to f capital of s. And here this is equivalent to g capital of s. And this, it is equivalent to h uppercase, okay, of s. It is also customary to use t which is the input function variable, for time as the variable of the input function, okay? And s for the variable of the transformed function, okay? So this is common also customary. So you can find that sometimes we put here instead of s, we put t. But for Laplace transform, we should always put s, okay? So this is only a notation. This is a common or a customary way for representing Laplace transform, okay? So don't worry about the meaning exactly, but just understand the significance of the lower and upper case in Laplace transform equations. Now, okay, let's go and have an example. Let A be any real number. A is a real number. And f of t, this is now small or lowercase f of t, this is the input function, and this is the input variable, equals to the exponential function e to at. The Laplace transform of this input function f is the function defined by, this is based on our definition, okay? So we are putting the new variable here, and then it equals to the integration that we have defined before, with the limits from 0 to infinity, e to minus s of t times e to at. Take care, this one is what? Exactly, it is the function. And this one is what? It is from the definition of Laplace transform itself. Okay, remember that if we go back, this one, e to minus st, which is this one, e to minus st, and times the function itself, e to at, times dt. Then we want to put this exponential function, then we can add or sum their exponents here, so it is going to be a minus s times t dt. We need to get what? Exactly, the convergence. When this integration, okay, we want to be sure that this integration going to converge. So we take the limit of this integration when k reaches infinity, and we put here the upper limit to be k for this integration. When you integrate this, we're going to find this is a limited integration, and we are going to find that this would equal to 1 over a minus s times e to a minus s times t for the limits between 0 and k. If we say that s is always larger than a, look to this exponent, s is larger than a. This means that when t has the k, which is infinity, then we are going to find this term is vanishing, right? Because e to minus infinity times t, this means that it is going to be very small, and 0. And for t equal to 0, e to 0, it is 1, and this would be 1 over 1 minus s. But it will be minus because we are having the limit, the bigger or the larger limit first, minus the value at the lower limit. So we're going to have minus here. And then 1 over 1 minus s, which is going to be 1 over s minus a. Right? Okay. Provided that, as we said, this is again, remember well that when s larger than a, remember that it is the condition for this. Because of this area, we have a minus s. This means that infinity here is going to cancel the value of the integration when we are dealing with the infinity or the larger limit. But when it goes to the lower limit, we're going to have the minus of the integration itself. The Laplace transform of f of t equal to e to at can be denoted as f of s, which is a new variable, equals to exactly this value, which is 1 over s minus a, but under one condition, that s is larger than a. Okay, so this is the first example that would help us in understanding what is the meaning of Laplace transform. Okay, Let's go and build our knowledge with Laplace transform. Okay. We rarely determine a Laplace transform by integration. Actually, what we have done before here, which is the integration and this stuff, we're not going to do it anymore. No need to make integration and this stuff. We are going to use some tables or a table that is going to help us. So whenever that we have something like e to the power at, then its Laplace transform simply is 1 over s minus a, right? This is what we're going to do. We're going to have a table 3.1. You're going to find it in the textbook, and I put it here for your knowledge, and we are going to look to it here. This is the Laplace transform table, which is table 3.1 in O'Neill book, and this is the most famous table that you can use for Laplace transform. This is actually Laplace transform for selected functions. Not all functions, but it is the most common functions that you are going to see in this course. So this is the input function here, f of t, and there are some entries here from 1 to 7 and the corresponding Laplace transform, and then another f of t here, continuous with the entries. Here stopped 7, here we're going to 8 until 14, and this is the corresponding Laplace transform. You are going to find, for example, one of the forms that we have used, e to at. It is going to be directly as we have integrated and got the value by integration. Remember that whenever that you see like n like this, for example, so n denotes a non-negative integer. And you're going to find some constants, which are a and b, like a and b, they are constants. Okay, so just remember about this in our curve. Okay. So table 3.1 is a short table of Laplace transforms of similar functions, and much longer tables are available. Actually, in literature you can find much longer tables. In this table, n denotes to non-negative integer, and a and b are constants. Reading from the table left to the right, so if we're going to read from the left here, from the left to the right, okay, so you can get the f of t here and the corresponding Laplace transform here. If f of t, for example, equals sine 3t, so then we need to find this. You will find it in entry number 3 here, which is, entry number 6. So we're going to find that entry number 6, it is sine at. It equals to a over s squared plus a squared, where a, it is the constant here. So if we have the constant to be 3, this means that our Laplace transform based on entry number 6, which is this entry, here, the table, then you're going to find that Laplace transform is going to be 3, which is a over s squared plus 3 to the power 2, which is 9. Okay. Now, if k of t, our input function, is e to 2t times cosine 5t, then we're going to search for this in the table. We're going to find it in entry number 11. I put it here as larger. E to at cosine bt, you're going to find equal s minus a over s minus a squared plus p squared. Well, what is the value of a here in our function? Here a is going to be, yes, exactly 2. What is the value of b here in our function? B, it is 5. So in this case, s minus 2 over s minus a, which is s minus 2 to the power 2, plus b squared, which is 5 squared, which is 25, right? So now we have our a and b from our input function, and we can get easily the Laplace transform from this nice table. Okay, I hope that we understood now what is the meaning of Laplace transform. Okay, Now let's talk about the linearity of Laplace transform. Linearity of Laplace transform. The Laplace transform is linear. What is the meaning of linear? Which means that the transform of a sum is the sum of transforms and that constants factor through the transform. What does it mean? If I have two input function f, lowercase, and g, another lowercase, this means that their Laplace transforms are going to be added. So we can put f uppercase plus g. And if we have one of the input function multiplied by a constant, this constant can be taken outside of Laplace transform of the function and they are equal. Okay? So this is an important characteristic of Laplace transform, which we call it the linearity characteristic. For all s such that f of s and g of s are both defined, and for any number c, this is we are talking about f and g. That's right. Okay, so now we understood what is the meaning of linearity of Laplace transform. Okay, now let's go to another type of characteristic for Laplace transform, which is the inverse. The inverse. Given f of s, this is f of s, we sometimes need to find f of t. Take care, what is this? Exactly, it is Laplace transform. Sometimes we have the transform in our hands, but we want to get what? The original function, which is lowercase f of t, such that L of f, Laplace transform of the original function is f. This is what we call it the reverse process of computing the transform of f, and we refer to it as taking the inverse Laplace transform. The inverse Laplace transform. Okay, this is denoted as L raised to minus 1. Okay, this is the meaning of the Laplace transform, or the inverse of Laplace transform. Okay, which means that the inverse of f capital here, take care, here is capital, then it would give us the small f, which is the lowercase f, exactly when the Laplace transform of the small f is f. For example, let's have an example here so that we understand how it works. The inverse Laplace transform of 1 over s minus a, so we have like 1 in the numerator and we have s minus a in the denominator. If we're going to search and investigate our table, we're going to find that entry number 3, we're going to find the f of s, Laplace transform of entry number 3 is 1 over s minus a, right? This means that it is going to be e to a. So in this case, we're going to read from the right to the left. Okay, in this case, we're going to read from the right to the left. Okay, I hope that you understand it well now. Okay, now let's go and have an example and see how we are going to deal with this. If we use table 3.1 to find an inverse transform, read from the right column to the left column. For example, using the table and the linearity of the Laplace transform, we can read that. Look to this. We have the inverse. We want to get the inverse transform of, this is the transform, plus or minus here 7 times another type. Take care, we use s here. They are s. This means that inside the parentheses we are putting our Laplace transform. Okay, so in this case we need to think about looking to this as one function and looking to this as another function. We have two functions and we said we have the linearity, then they are added to one another. Then we can look to this term individually. 3 over s squared plus 16. Can you guess which one from the table? If you go to the table and surf the table, you're going to find entry number 6, that reading from the right now, we're reading from the right. It is a over s squared plus a squared. This means that very similar to our case, but in the numerator it is 3, and 3 squared is not here, right? That's what is happening now in your mind, right? Actually, this can be something like this. We can put it like this. We can say in the denominator it is s squared plus, if I'm going to put 4 squared here, which is 16, which is this 16, and the numerator I'm going to put 4, right? This actually would equal exactly to this form, but it does not equal to 3 here, right? So we're going to multiply here by constant. As we said, we can have a constant. This constant, the denominator of the constant is 4, to cancel this 4, and the numerator is going to be 3, right? And this is actually what we have done here, which is 3 over 4 times what? Times sine, because this is the input function of it. So it is 3 over 4 times sine 4t. Take care that this is a, which is similar to a here, similar to the 4 here, right? So now we have finished the first part, which is this part. Now let's go to the second term here. It seems to be complicated. Look to something in the table, reading from the right, as we said, something that its denominator is 2 terms multiplied by one another. Going to the table, okay? Going to the table. I'm going to the table here. Look here, looking to the table, reading from here, okay? Reading from the right. So we read from right to left, as we said. Looking here, something multiplied by, yes, here. In the denominator, things 2 are multiplied. I think that if you check and investigate all of them, you are going to find this is the only one. Like s minus a times s minus b, right? And the corresponding is EAT minus e to bt. Well, this might help us. Let's go now to our example and investigate what we were doing. Yes, we have s minus 5. So this means that we have here s minus, if we look here to this entry, s minus a, which is s minus 5. This means that we have we have now a equal to 5, okay, and then s minus 12, which is s minus 12. This means that we have b equal to 12, and in the numerator we have a minus b. This is a minus b. So we have a, which is 5, minus b, which is 12, right? 5 minus 12, it is minus 7, right? It is minus 7. So I think that it's similar to this. This is 7 here, which is a minus b. And we are going to have 1 over s minus 5 times s minus 12. This means that our function is going to be the exponential function. The exponential function, which is e to at minus e to bt. And this is what we're going to put it here. Exactly, e to 5t minus e to 12t. Okay? You understand it now? I hope that you could understand what I have explained. So the inverse Laplace transform is linear because L is linear. As we said, this is linear. Linear means that we are adding up 2 functions together. So no problem now. The functions are going to be also linear. This means that Laplace transform, the inverse of Laplace transform, is going to be the summation of the inverse of each function alone, which means that f plus g. Okay? So now this is how it works for for us and how you are going to use the table. How you are going to use the table. Okay, now let's go to, and this is actually, you can find it in the table as I said, entry 5 and 6. Okay, now let's go to some in-class assignment, and I hope that you can work them well. Okay, I hope that you can work them well. Okay, now as usual, you are going to look to the equation and then you are going to work it by yourself first. Then stop the video here, look to this, which is the problem, and look to this only. Okay, and after that, you stop the video here, try to solve these equations by yourself, find the transform, Laplace transform of them, and then come back again to the video. So after coming back, you are going to find that we have a function here, which is w of t equals to cosine 3t minus cosine 7t. Then we can go to the table, find Laplace transform for this function. From table, from entry number 7, this is entry number 7 in the table, cosine 8t, this is cosine 3t. So this means that we are having it as s over s squared a squared. So we are going to say cosine 3t, its Laplace transform is s over s squared plus 3 to the power 2, which is 9. And we have minus, which is going to be minus here as it is, and then cosine 7t, cosine 7t, the same entry. We're going to find s over s squared, a squared, but it is 7. So we are going to have 49 here. S over s squared plus 49. This is the Laplace transform of this function from the table. From the table. Okay. Now let's have another problem. In this problem, we are going to find that this is the equation that we have. K of t, this is the function that we have. This function is minus 5t squared e to minus 4t plus sine 3t. Okay? So this is the function that we have here. Okay. Now, let's go through this. We want the Laplace transform. There are two functions here, t multiplied by exponential function. Can you serve the table? So if you go through the table, we're going to find entry number 4, we have t to the power n times e to the power at. So we have this. Don't worry about the constants because we are going to deal with it later. Now, the most important thing is what is a here and what is n and what is a, right? So here it seems that our n, it is the exponent of t, which is n is going to be from here, it is, sorry, n is going to be 2, and a seemingly to be minus 4, right? It is minus 4 here, this one. So this means that we can put our Laplace transform as the form of entry number 4. This form, right? This form means that n factorial, so we have the factorial of 2, this means that 2 factorial times the constant from outside, which is minus 5. Already we have this minus 5 from outside, over the denominator, denominator, which is s plus 4, because s minus a, it is as if s minus minus 4. So it is s plus 4 raised to the power n plus 1. N, already we said n, it is 2. So it is 2 plus 1, which is 3, which is here. So minus 5 times 2 factorial, it gives us minus 10. And in the denominator, it is s minus minus 4, which is plus 4, to the power 2 plus 1, which is 3. So now this is the first part of the equation that we have solved. It is okay for us now, right? Okay, now let's go to the second part. Let us clear this first. Yes, now let's go to the second part, which is sine 3t. I think it's easy for you. Using entry number 6 and the linearity of the transform here, the linearity because of the minus 5, but using entry number 6, this is entry number 6 here. Right, sine at, so we have a over s squared plus a squared. Here it seems that a equal to 3. This means that we have 3 in the numerator. Here s squared plus 3 to the power 2, which is 9. Okay, so this is the Laplace transform of this equation is going to be this one. Okay. Okay. So now I think that we are ready to go to a home assignment that you are going to do. Let's go now to explain our home assignment. So first of all, for the home assignment, sorry for this. Okay. I think that there's some problems here. So for the home assignment, it is, I don't know why it doesn't work. Okay, for the home assignment, we are going to have, sorry for this, it doesn't work, but I'm going to post, you are going to find the home assignment in the PDF file. Okay, so I think that it would end us here.